This is a spring mass damper system, and it's actually a second order difference equation, and also intuitively explains why we need both the solutions and why we have two initial conditions and all that fun stuff. Let's get started. So it's a spring, it's a massive damper, which pretty much means friction. So here we have a wall, we have a floor, there's a mass, it's attached to a spring on the wall. It's got an initial position of 3 meters. By the way, the rest position is 0 meters, so if you put the block there and you don't move, it doesn't have a velocity, it's just going to stay there forever. It's the rest position of the spring. And so now we want to predict what's going to happen in the future. This block is at 3 meters to the right of the rest position, and it's going to the left at -2 meters per second. And so this block, it has a mass of 1 kilogram. The constants end up having somewhat strange units, but the friction is 5 kilograms per second, and the spring constant is 6 kilograms per second squared. We also have the starting position is at 3 meters, and the starting velocity is at -2 meters per second. If we actually write this out as a differential equation, it ends up being z double prime plus 5z prime plus 6z equals 0, where this piece is the friction. That's the spring. And then this one is F equals ma. Force equals mass times acceleration. They all end up having the same units because of the constants, and all of the forces acting on the block have to cancel. That's why they all sum to 0. We also have our initial conditions. We have z at time t equals 0 is equal to 3 meters, and z prime at time t equals 0 seconds equals -2 meters per second. So now the reason we need both of these is, if I didn't tell you let's say I didn't tell you either one, I told you to predict the future of the position of the block, you couldn't do that if you had no initial conditions whatsoever. You didn't know where it started and you didn't know its velocity. All right, well, what if I had told you just one of them? What if I had told you just z of 0 equals 3, and I didn't tell you the velocity? Well, you still have no idea what it's going to do, because depending on the velocity, it's either going to be going left when it's to the left when it starts, to the right at the start of the experiment at 0 seconds, or if z prime equals 0, it's going to have a velocity of 0, kind of stay exactly where it is, and then start moving. So you need both of these to be able to predict the future of position of this mass on a spring. So physically, that's why we need two initial conditions, a z and a z prime, for a second order ordinary differential equation. There is a math reason as well that you can kind of reason out, but it's not as intuitive. Physics, people tend to get that pretty well, mass on a spring. And then because we need both initial conditions, that's also going to highlight why we need both of these solutions that are fundamentally different from each other to solve the differential equation, this initial value problem. Let's go ahead and get started. Well, so our guess, as always, I'll make a room. So our guess, as always, is z of t is equal to e to the r t. And so if we use that and we plug it into the differential equation, we have z double prime plus 5z prime plus 6z equals 0. Well, that'll turn into 1r squared plus 5r plus 6 times e to the r t equals 0. And then we have to factor this to get it to, to find our individual solutions, z1 and z2. Well, that one factors into r minus, r plus 2 and r plus 3. Yeah, it looks right. So 2 times 3, that's 6. And then with the inner outer, we have 2 times r plus r times 3 equals the 5r, and then we get the r squared. So our solutions, z1 of t is equal to, e to the -2t, and z2 of t equals e to the -3t. So then the general solution is z of t equals, c1 z1 plus c2 z2. Well, that's c1 e to the negative 2t plus c2 e to the negative 3t. All right, well, we have the general solution. Let's go ahead and solve the initial conditions. So we know that z of 0, we'll plug in 0 to this thing. We get e to the 0, and we get e to the 0, so it ends up being just c1 plus c2. c1 plus c2. We know that is 3 from the initial condition. That's one equation. The next one, we do have to compute z prime. So z prime of t equals, all right, well, it's negative 2 times c1 e to the negative 2t, then a minus 3 c2 e to the negative 3t. And then we get to plug in z prime at 0. All right, that's not so bad. We get negative 2 times c1 times 1. We get e to the 0, which is 1. So negative 2 c1. And then same thing here. We get e to the 0, so we get minus 3 c2. But we also are told from the initial condition that z prime, when t equals 0, is negative 2. And so now we have two equations to solve with two unknowns. We've got c1 plus c2 equals 3. We have negative 2c, forgot the 1 there, negative 2c1 minus 3c2 equals negative 2. All right, well, I want to add 2 of the top equation and then to the bottom equation. So if I do that, I'll end up with, 2 times c1 plus negative 2 times c1, that'll be 0 c1 plus, and then I have 2 times c2 plus negative 3 times c2, that's actually a minus, let me get that, minus c2, and then I have 2 times 3, well, that's 6, and I add 6 to negative 2, that ends up being 4. And so from there, I have negative c2 is equal to 4, and c2 is equal to negative 4. Then from there, we can go back to the easier equation. Right, so we can look at c1 plus c2 is equal to 3, but then I know c2, so I have c1 minus 4 equals 3, so then c1 is equal to 7. So the general solution, this is the general solution. The solution to the initial value problem of the spring mass damper system is z of t equals 7 times e to the negative 2t, and then minus 4 e to the negative 3t. All right, so intuitively, right, we have the second order differential equation. We needed two initial conditions, a z and a z prime, a starting position and a starting velocity, in order to predict where the future position of this block attached to a spring is going to be. And then in order to be able to solve for both these initial conditions, we needed both of these functions here that actually solved the characteristic equation. We needed the e to the negative 2t and the e to the negative 3t. So intuitively, that's why we add together these solutions with c1 e to the r1t plus c2 e to the r2t, the two roots.